Hello, everyone, and welcome to my talk. My name is Arun Kumar. I'm a faculty member at the University of California, San Diego, in both computer science and data science. Thank you for having me at the KDD Deep Learning Day. It's great to be here. I'd like to share with you some thoughts on what I see as some damaging delusions in deep learning practice and deep learning systems and how to avoid them. A little bit about my research. I'm not in the deep learning or machine learning world. I've never published at any of the ML venues. I publish primarily in the data systems world. I work on new abstractions, algorithms, and software systems to help democratize ML and AI data analytics from a data management and systems standpoint. By democratization, I mean improving the efficiency of the systems and the tools and the algorithms, reduce their resource costs, and also improve the productivity of the practitioners involved, the data scientists, ML engineers, and others. I really bring together these worlds of data management and databases and principles from those worlds and straddle the whole system stack to help democratize ML and AI. More precisely, I build practical and scalable data systems for ML analytics that are inspired by the principles of relational database systems that we've been studying for almost half a century now. But I exploit insights from learning theory and optimization theory also, which are at the root of what ML computations are about. So why am I here to speak at the KDD Deep Learning Day? I want to share a little bit about two kinds of delusions that I'm seeing, modeling related and systems related. But first, some background on what we've been up to in the large scale DL space. We've been collaborating with public health scientists here at UC San Diego for almost 3 years now in building deep learning models to predict activities from time series data, from accelerometer data that are almost a terabyte large, labeled data that they have had, that they have collected. They had prior hand-tuned physics-based features and random forest models that gave some 76% balanced accuracy for a binarized version of this prediction classification task. We built deep learning models using state-of-the-art CNN and LSTM hybrids that gave almost 92% accuracy. This is now the state of the art in their field. We published about this in public health journals. How did we achieve this lift? Our secret sauce was not fancy ML algorithmics, new model architectures or whatever. We just did model selection with deep learning tools that was done with a high throughput manner so that we could explore different configurations and achieve this sort of lift. We found that the parallelism of the existing systems was a poor fit, and so we set about on this journey to understand DL system scalability. My friends, the reason I'm here today is to bust many DL delusions and to slay DL practices so abysmal, DL systems so dismal, they even turned my hair gray. Let's start with some modeling delusions. Now, all of you are applied ML experts here at KDD. You know that the test error can be decomposed into bias variance and base noise, where the bias variance trade-off is determined by the complexity of the model's hypothesis space and the feature space as well, between underfitting and overfitting. Test error varies non-monotonically. But more recently, we saw in the interpolation regime, where the model complexity grows even higher, especially in deep learning, test error can actually go down even more if you're able to afford a lot more complexity. Of course, the base noise is something that no model can mitigate because of discriminability of examples. Model selection to tune these bias variance noise trade-offs is inevitable in any applied ML task. You need to configure data representation, neural architectures, and hyperparameters. That is how you navigate this trade-off space. We saw the same thing in our public health use case. So we had trained different kinds of models, almost 100+ models, varying all these sorts of hyperparameters. Here's the simple snapshot that I'm showing here that shows 2 different clusters of configurations leading to different accuracies. And the ones at the bottom are the ones we ended up picking. Later, we got more label data from a different cohort. So we are working with different cohorts of people who are breast cancer survivors, people with obesity, people from assisted living facilities, and so on. And so in this second cohort, we thought we could amplify the capacity even more to maybe hit the interpolation regime. Turns out it was much harder than we thought. Even after amplifying the network many times, it didn't actually go into the interpolation regime, and it was just so much slower to train, much more painful for them to deploy on new cohorts. So it's not easy to achieve this. Now, in the model selection practice in real world, we have these surveys of people at New York and Eichler. They say some of them do optimization, some of them don't. But this what really caught my eye. I mean, like many of them do manual tuning. Oh my God, people, is ML even a science anymore? If you're just hand picking some random hyperparameters, just taking numbers out of a hat, that is not how it's supposed to work. You need to do rigorous model selection with proper hyperparameters. Thankfully, I think AI conferences, ML conferences are now starting to realize this and demanding this from authors. But it does make for a lot of trolling. If I had a dime for every time this happened to me, I would be a rich man by now. Anyway, another propaganda I see is like, now, label data is all you need. Just keep accumulating these vast barrels of oil. You know, label data is new oil. But all this oil is of no use if your cart doesn't work properly and if it's really sucky. You might as well just move your oil around in donkey carts. Rigorous model selection is how you ensure you do not squander the label data that you've invested so much time and effort in for your application. To summarize, model selection is often ignored by DL types. In the worlds of ML systems, databases, all stripes, are they deluded or just lazy? Or just marketing like crazy? Boy, for sure they are living stereotypes. So to avoid this delusion, perform rigorous and repeatable model selection to optimize task-specific bias variance noise trade-offs. Moving on, there's this new propaganda that AutoML is a savior. Everything will be fixed with AutoML. Actually, the AutoML heuristics are indeed useful in many cases, but they're often very easy to abuse. I've seen so many cases where they said, oh, we use AutoML to tune everything, but then ended up burning through $1 million just to build one model. I imagine everybody doing all of this, it's not going to be economical. You need the prudence of human intuition to prune the search space and specify what to search and what to use for AutoML. And that is how you avoid this delusion. Hybrid human in the loop plus AutoML specification to rein in this bloated use of resources that takes place often with AutoML. Moving on, transfer learning is another new propaganda where they say it's the new savior. Entire deep learning has been solved with transfer learning. Actually, if you look closer, task-specific bias variance noise trade-off do not disappear. You still need to do it. Model hubs, Hugging Face, and all these sorts of libraries are indeed helping democratize state-of-the-art deep learning models like transformers and others in many fields. But the world is far, far bigger than just a few natural language processing or image processing tasks. Now you might wonder, what does transfer learning have to do with model selection? Literally everything. Pre-trained models are just seeds for the featurization, for data representation, for fine-tuning of parameters and so on, and architectures. They help raise the bias, but reduce the variance in the overall mix to reduce the test error. So you have to do these sorts of model selection here. Now, in many cases, you have multiple modalities of data that need to stitch together. That leads to bespoke bias variance noise trade-offs that are task specific. So transfer learning is rigorous. It must be rigorously treated as another part of model selection. That's how you avoid this solution. Now, all of this model selection talk must kind of make you think, oh my God, I have to train so many models. It's so painful. And I've seen many deep learning users complain about how their deep learning system fails to scale and how it's really miserable to use at scale. That's where I'm going to talk about some systems related delusions. So many DL systems are so poor at scaling. One wonders why there is so much failing. Boring, wasteful execution is not really a scaling solution. Against DL systems, I will now start trading. Now, what do I mean by boring, wasteful execution? We saw that most of these DL systems today use one of two paradigms. First is task parallelism. That's used by things like Ray, Google Vizier, DAS, Celery, Asha, Determine, and so on. They place different model configurations on different workers, and they copy the entire training data set to every worker, and then they train them in parallel. On the other hand, you have data parallelism tools like Horovod, Parameter Server, and I think Eric also talked about Petum, they're Autodesk. They work on sharded data, and so they run one configuration on the entire cluster at a time, and then they run configurations one after another. Now, they have pros and cons, and in the task parallel world, you get high throughput because you train many models in one go. You get the best possible SGD accuracy because it is sequentially equivalent, but it's really poor on data scalability because you're literally copying a data set across all workers. Like in our case, if you take the 1 terabyte data set, it'll bloat to 10 terabytes if you use 10 workers on a cluster. You're wasting memory and storage. Now you could read from remote storage like S3 and repeatedly read every epoch, but you'll be wasting the network by almost 100 to 1,000 times because of the iterative nature of SGD. On the data parallel side, you get high data scalability, so you mitigate those issues. However, you end up with really poor throughput for model selection because you're training one model at a time, and there's enormously high communication costs going on because models are shipped and parameters are shipped at every mini batch level, and that could be even 10,000 times slower than otherwise. So we saw this landscape, these two monsters duking it out, and we came up with a new technique, model hopper parallelism, a hybrid that beats both of them out of the water. We published that in the system Cerebro, and this is a basic idea of how model hopper parallelism works. SGD, this is the insight we use from optimization theory. SGD does not care what ordering you visit the data in as long as it's some random order. So you shuffle the data set and shard it across the workers, just like in a data parallel setting. But now you start your first epoch with different model space on different workers. So it's just like your task parallel setting. Look at your local shard, checkpoint, hop to the next worker, and then start continuing the training on the next shard. So that's the next, what we call sub-epoch. All models keep hopping across all the workers, and they see all the shards of T for one epoch. Repeat this for every epoch. This is why it's called model hopper parallelism. There are strong theoretical guarantees here. Every model is trained in a sequentially equivalent manner, and therefore you get the best accuracy comparable to test parallelism, but it hits the lower bound on communication costs for model selection on sharded data. And so it's very data scalable. Now, again, feel free to take a look at the papers on the Cerebro project webpage if you're more interested in this. We are also coming up with a suite of new hybrid parallelism techniques for all kinds of scalability bottlenecks in deep learning on all axes: data sizes, number of tasks, number of groups, model sizes, and so on. More recently, we published about building separate models for separate groups. How do we make that scalable? We came up with hybrid techniques there. Model scalability for GPU memory being limited, beating model parallelism and task parallelism, we came up with new hybrid techniques as well. So keep an eye out for all these sorts of new DL systems techniques in Cerebro. Summarize, hybrid parallelism scales so much better. It may even become a new trendsetter. Data, tasks, models, all are on. Boring scaling now be gone. Free DL systems from every scaling fetter. So that's how you avoid the first systems illusion. DL systems need hybrid parallelism to scale well. Moving on, now if you look around, the big tech companies, the big AI labs have this gospel of gluttony. They want to throw more GPUs, more memory, more machines, more this, more that. That's like hundreds of machines, thousands, millions of GPUs. It's like they want to burn the planet in holy GPU fire. Now, these cloud whales, as we call them, do indeed help democratize access to resources like GPUs. But there is a conflict of interest that you should be aware. Pay-as-you-go is a double-edged sword. These cloud whales feast on the money that these enterprises and small web firms pay to them by renting resources. And so they have basically, you need to focus on overall resource efficiency and reducing costs. But how do we ensure that can be done? How do we optimize resources holistically? In the database systems where we have these history of query optimization being at the heart of ensuring holistic resource efficiency to help reduce costs. And in Cerebro, we are bringing the analog of that to the scalable deep learning systems world to ensure holistic resource efficiency and reduce costs. Just throw more machines, says a greedy sneer. Money or energy concerns, who cares, dear? Cloud whales hunger for ka-ching. Optimizing systems ain't a thing, but we see through their folly and jeer. So to avoid the second systems illusion, DL systems need query optimization to raise overall resource efficiency and reduce resource costs. With that, I'll stop. These are my terrific students at UC San Diego that are building out Cerebro, and they've been doing spectacularly. Supun is on the job market later this year. Feel free to drop us a note if you're interested in recruiting him. With that, you can take a look at all of our papers, demos, talks, code, data. Everything is there on the project webpage, on our group webpage. Also, feel free to follow me on Twitter if you want more frequent updates. I'd like to thank all of these sponsors of my group's research. And I'll end with this summary slide. All deep learning folks, wake up and smell the coffee and avoid falling into the trap of these delusions.